we found interaction energy del capital W. Okay. So this is interaction energy. Here we have electron in this elliptical orbit. We know this electron revolves around the nucleus in elliptic orbit. So we have to calculate the average value of this quantity 1 by RQ. This one. Okay. So we have to calculate its average value because it is elliptical orbit. Okay. Now by using the perturbation theory, okay, we will see the perturbation theory in detail. So in quantum mechanics, we know the perturbation theory. According to this, we have the value of 1 by RQ as, say, Q by A1Q, where A1 is the first Bohr radius. Okay, it is a first Bohr radius. Then NQ, you know, NL, then L plus half. Sorry, it's 1. Okay, and L plus 1. All these equation numbers, okay, we will use this equation to put the value of 1 by RQ. Then here we have the value of A1, that is first Bohr radius, which value is epsilon naught h square by pi m e square. So this is first Bohr radius. We know the Bohr radius. So it is first Bohr radius. So we can put these two values in this equation and we will get the interaction energy. Now consider the diagram. So just remember these equations. Now consider the diagram. Here we know we are using vector atom model. Okay. Here we are considering the vector, the directions of each spin and orbital motion. Okay. So consider this precession of vector of electron. Sorry, vector of the spin of electron. Okay. This first one. Call this, show it with arrow, as it is a vector quantity S. Now for S star, we know this. So this S is precessing. Okay. So S is what? S star, we know it is angular momentum. So we are using vector atom model. So it is shown by the vector. It is precessing about its resultant J star. We know this. So it's J star. Now consider another one. Obviously, it is vector of orbital angular momentum L star. So show like this. So we got two angular momentum vectors. Here it is. This another quantity is also vector. So this represents the precession. Okay. This is precession of a spin angular momentum vector, and this is precession of an orbital angular momentum vector. So in book we have used the vector log addition like this. You can use this vector here. So like this. This is the resultant. We know this parallelogram. Okay. So this is the resultant. This is simple. So just erase it. It's just for calculation purpose. This makes good understanding. Okay. So this is spin angular momentum vector. Precessing around the resultant J star. This is orbital angular momentum vector of an electron. So we are using vector model. So we are representing it with a vector. So this is it. Now we need to calculate okay. First we will calculate the complete interaction energy using these three equations. So as we write it directly, because we are just putting the values of 1 by R2 and A1 in their place. Okay. So the resultant value of capital W will be say power 4. You can calculate this on your own. So simple. 32 epsilon naught power 4 c square h power 4 h Planck's constant, then L star S star cos L star S star divided by n cube L plus half L plus. So this is the result of interaction energy. Now we have to calculate the term shift. So what is term shift? We know what is term shift. We know atomic spectral line splits into two. Okay, we are studying only the plates. Okay, for our syllabus. So that was the supposed line. Now it has shifted. It has term shift. That means this value tau another. Okay, so these are tau and tau 2 you can say. Okay, so this shift is a term shift and it has some value. So we are calculating. We are going to calculate this value now here. Okay. So let's calculate this term shift. Okay, right here I have paper. So let's calculate term shift. We represent term shift in wave numbers. What is wave number? It is nothing but a spatial frequency. Spatial frequency. You will get this term wave number in atomic and molecular physics very frequently. Okay, so what is wave number? What is spatial frequency? It is nothing but waves per unit distance. Wave cycles, vibrations per unit distance. We know another frequency, that is temporal frequency. That is our regular frequency. Temporal frequency, which is nothing but we know waves per unit time. That is second. Okay. So wave number is spatial frequency. That means with respect to distance, waves or vibrations or cycles per unit distance. Now our regular frequency, temporal frequency, which is nothing but waves or vibrations or cycles per unit time. So we are representing the term shift, that is del t or minus tau, which is equal to minus of del capital W, that is our interaction energy, divided by LC. So this is term shift in terms of wave number. Okay. Now we are calculating term shift. So we just have to divide the interaction energy with LC and we will get the term shift in wave numbers. Okay, I will write directly. Z power 4 m e power 8 divided by 32 epsilon naught power 4 c cube h power 5 h Planck's constant L star cos L star S star. This is nothing but angle. You know this cos L star S star n cube L plus half L plus 1. So that will be term shift in terms of wave number. Now we have given the values for some quantities like this. I will rather note down this wave number. It will come very frequently in atomic and molecular physics. So we are considering R, that is Rydberg constant, n e power 4 by 8 epsilon naught square c h cube. This is Rydberg constant, alpha or alpha square, let's say e power 4 fine structure constant. This one is a fine structure constant. Now the last one. Okay, that's the last one. So we are putting these two values in this equation and reducing it. So we can put value of r and alpha square here. So we get tau is equal to r alpha square z power 4. Putting this and this value here. So 1 here is n cube L plus r L plus 1 L star S star and angle between them cos L star S star. Now we are calling this term, the whole term as A, small a. Don't confuse with the first board radius A1, which is not equal to this one. Okay, it is a separate quantity. We are just saying it A. Now that A1 was a first board radius. This is nothing but just a constant. Okay, we are putting this value, the total terms value A. Now here, okay. Now this we can write as this angle of the total term L star cos L star divided star L star is equal to J star square minus L star square minus S star square by 2. So we can put the value of that term there. So putting this value, we will get term shift term as A by 2. Here this A, that half, and A star square minus L star square minus S star square. So using this, we can calculate the term shift term value for each fine structure doublet. So finally, we can represent the term value of fine structure level as capital T is equal to tau naught minus tau. So this is our term shift here. What is this quantity? It is a hypothetical center of gravity. We have shown this fine structure doublet here. Line splits. So a central line is nothing but a hypothetical center of gravity. Tau naught. Okay. Tau naught. So this shift in energy level is nothing but term shift. Okay. This is tau naught. This is term shift. So this is resultant term shift or term value. Okay. This is term value, term shift, and hypothetical center of gravity. This line shows hypothetical center of gravity for a doublet fine structure. This is term shift, nothing but tau. Yes, tau 1, tau 2, you can say. Those values are different of sign. So this is the hypothetical center of gravity. This is term shift. Okay, tau. And then we will get the final term value. Don't confuse with these values. This is term value. This is hypothetical center of gravity for doublet fine structure. This is term shift. So using tau, that is term shift, you can calculate the separation between this doublet fine structure T0 from T0, the hypothetical center of gravity. So we can calculate using tau. This is nothing but term shift, the tau. So we can calculate the separation of doublet fine structure from this center of gravity. Let's calculate for S electron. obviously it is a state. In single electron, we will have the Electron spin angular momentum value half. Then obviously the value of J will be only 1, it is half. Single value of J. So using the formula for tau is A by 2 and J star minus L star minus S star. So we don't have to write the complete value of A. So just calculate these three. We know what is the L star under root L plus 1. So calculating using this, we can calculate the value of tau for S electron, which is 0. So tau is equal to 0, that means no splitting of S state. We know this. S states are singlets. Okay. So tau is equal to 0, that means no separation. So that's correct. Okay. S state. So that was for S state. S electron in S state. Now let's calculate for P electron. Then S values of J. For P electron, what is that? That is 1, S is half. Then values of J are, L plus S, up to L minus S. So half and V by 2. So for tau, value of J is half, so value of J is 3 by 2. We have to calculate two term sheets. Okay. See here, this is main cycle line, it is splitting into 2. We have to calculate this tau 1, this tau 2. Okay. Now here we have P electrons, so at upper level will be P 3 by 2, the lower level will be P half. So we know this splitting. Now we have to calculate the term sheet values. Here, tau half I will write directly, you can put values of L, S, J in this formula and get the value of term sheet in terms of A. So what is the value for first one? It is minus A, it is tau half. The second one is half of A. Okay. So we can show this using this diagram here. Tau 1 will be minus A. Okay. So minus A. This one is A by 2. So when you show in a diagram, you show this upper level half of this lower level. Okay. This width should be half of this. Why this as there is minus sign, this low below the hypothetical center of gravity. Okay. This is upper because it is a positive one. You can understand this. So this is the separation. We calculated the term sheet, the energy of separation from this formula. Okay. So did you understand why we derived this formula for this purpose? Okay.